This being an NLP talk, let me start with some poetry. We have also obtained a glimpse of another crucial idea about languages and program design. This is the thing which I greatly feared is come upon us, desolation and destruction. Now, if that particular passage doesn't make any sense to you, that's okay. It was generated by a language model, a Markov chain in this case, that was trained on the Bible and a programming book called The Structure and Interpretation of Computer Programs. Yes. There's more of that at that address. If you're interested in seeing what comes, there's lots of interesting quotes there. But of course, so that language model isn't really meant to do anything particularly useful. It's mainly for fun, possibly for learning for the author, who is not me. But this idea of language models has fairly recently, in the last sort of 12 or so months, gained quite a lot of attraction in the NLP community, because what's been dubbed sort of the ImageNet moment of NLP, the NLP community realized that we can actually use the language models as a basis for training all kinds of other models for all kinds of other tasks in NLP. That has led to somewhat concerning headlines. This particular one is related to the non-release of a language model from OpenAI, a private research institute, where the researchers there were specifically concerned that the model is good enough in generating text that a bad actor could use that model to generate sort of posts and text in online forums and sort of replicate or create a community around some concept or some idea where that community doesn't actually exist. Think of, I don't know, fake news for political purposes, for instance. Okay, so what's going on here? I'll try to, in the next, I don't know, 17 minutes, kind of go over what's been happening in the research field in NLP over the last roughly 12 months, and specifically give you an intuition as to what these language models are, and then look at how we are deploying those into production, how we're taking these research efforts and putting them into production at Comtravo, where I work as a research engineer. So what's been happening in research? This is a snapshot of research results for machine translation. This particular one is for English to French. And you can see a kind of an uptick there around sort of beginning of last year-ish. Similar, this is English to German, not quite the same sort of uptick, but still the curves are going up, which is nice. This is question answering. There's a very, very significant improvement suddenly in within the space of, this is July 18 to about now. Right, so that's less than 12 months, and we've added about 30% to the performance. And then finally, language modeling itself. This GPT-2 model that you see here, this is the specific model that the OpenAI researchers decided not to release because of its capability of producing convincing language. Okay, so what are language models? So if I were to say that they're kind of models that are, in very, very general terms, just trying to predict the next element in a sequence. This being language, and there being language models, that sequence is words, and the next element in that sequence is the next word. So if I'm going to say, I bet you can't guess what I'm about to say, then you might reasonably claim that the following word is going to be next with possibly a chance of 12%. I'm unlikely to say apple following that sentence. This is kind of the very general idea about language models. So why is this useful as a way of kind of capturing language and using this learning process as a basis for other kinds of NLP tasks. Why would this help me do document classification? Well, if we if we look at a little bit more complicated or a somewhat more different sentence. The train up to Hamburg today was really slow, but I had time to enjoy the scenery, versus, but it was also uncomfortable. Now the second sentence there, the red sentence there, seems somehow wrong, because the conjunction but is supposed to introduce some kind of a contradiction in terms. So it's supposed to reverse somehow the sentiment of whatever the first part of the clause is. But the two parts in the red sentence have actually the same sentiment. And the same if you are inclined to speak German. Doch is a good example for this in German. It's doch is supposed to kind of negate whatever some other person just said to me, and I go like, no, 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 no. So in order for the language model to learn to predict what the next word after but is, or the next words after but is, it has to not just be able to memorize some sequence of words, but it has to actually learn something about the grammatical role that the words play in the sentence, and how those impact the semantics and so on and so on. How do these models actually work, and how are they then deployed into production, or like deployed into other tasks? So this is a picture from a paper called Universal Language Model Fine-Tuning. The two columns on the left depict the sort of language model itself. So you have a neural network of some depth. In this case, they have the three middle layers are a recurrent neural network. They're just three identical recurrent neural networks stacked on top of each other. And you train that. That takes a very, very long time, but the idea is that within those weights, within that stack of recurrent neural networks, you've internalized something about the language that you happen to be looking at. And then in the final column on the left, yes, sorry, on your right, my left. They change, you change what the model is supposed to be doing. So you take out that last layer, but you keep everything else. You keep all of the knowledge that the language or the model has learned about language, and then you swap out the last layer and you say, well, now you're not predicting the next word anymore. Now you need to predict the class of a document. Is this positive sentiment or negative sentiment? Is this a booking or is it not a booking? For instance, this is one way of doing it. There's another way of doing that, which is to say that we don't keep, we use the language model as just a feature extractor. So this is a paper from Zalando Research, and what they do is the character language model that you see there on the bottom, that is used as a feature extractor to create word embeddings and then document embeddings, which are then fed into just a regular sequence model. But the language model, once you transfer that, once you've trained the language model, it's sort of not part of your prediction task anymore. You're just using it to get some kind of a representation of the data that you have, which you then feed to a separate classifier, predictor, or something. There's a really, really good blog post, by the way, the bottom link there by Lillian Weng. She goes through all of these different sort of ideas and different implementations, and there's links to all of the different papers. I don't have all the papers here, but that blog post, it's a long read, but it's worth looking at. So, okay, so how does this translate into production then? Let's start with what Comtravo is and what we're actually trying to do. So Comtravo is a business travel agency. We get bookings via email from our customers, and we want to do an end-to-end automation pipeline where upon receipt of an email, we run that email through the pipeline and we get an offer which we then return or send back to the customer, usually, hopefully, within a couple of minutes. So in this case, where the customer is requesting a hotel for a famous Finnish footballer, for mid-May. Now, of course, this is not quite as simple as just sending out the offer. So my work focuses mostly on this NLP part here. And the NLP is feeding data, and we need to talk to a lot of external APIs and blah, 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 blah. So what the NLP is supposed to do is extract the relevant bits of information from the email and formalize that into some kind of a request that we can then feed into the search engine. Formalized request might look something like this. So we've nailed down that it's a hotel booking, we know where it is, we know which hotel you want, we know when you want to go there, how many rooms you want, do you want Wi-Fi, do you want parking, breakfast, not breakfast, and so on. Not all of this information is necessarily always in the messages that we get. Not all of this information is necessarily always required. If you don't tell us when you would like to book the hotel, it's going to be difficult for us to do so. But, I mean, we don't necessarily need to know if you want Wi-Fi or not. The same obviously applies for flights. The destination of a flight is relatively important, whereas, I don't know, your frequent flyer number, it's a shame if we miss it, but it's not the most relevant piece of information. And then, of course, there's always the messages. There's always the possibility that the messages contain more than just a single booking request. In the request above, the idea was that you get either this hotel or that hotel. So we need to be able to represent combinations of requests per message. So how does then the research translate into this task that we need to do, this information extraction task? So let's try to put a little bit more meat on this. So this is now a different request, but this is what a machine translation task could, for instance, look like. So you need a morning flight from Berlin to Helsinki early on the 10th, or an afternoon evening flight after 6 p.m. And then you'd also like a hotel, and you want the flight back on the 12th. We can try to formalize that as a sequence-to-sequence prediction task. So the machine translation models usually try to consume some kind of an input sequence, which in this case is our message, create a representation of that, some kind of an embedding within a neural network, and then from that embedding, not from the original sequence, but from that embedding, from that representation, produce some output sequence. And in this case, our output sequence would just be the kind of formalized slots along with the relevant bits of the text that go into those slots. There's a somewhat obvious problem here, which is that we don't actually care what the order of the output sequence is. I don't care if the model outputs the departure of the flight before the origin of the flight, or the departure time before the origin, or if the destination comes before or after the origin. Because they are formalized, I can tell from the output how to then process that further and feed that into whatever system I need to feed it into. But that's a sort of a bad fit, because the sequence-to-sequence models are optimized in such a way that they are sensitive to the order of the output sequence, whereas in our case, we're not really. I mean, partially we are, but not really. So we would need to somehow at least change the loss function so that it becomes not anymore sensitive to the sequence or to the order of the output sequence. But then it's questionable whether we should be using that model in the first place or not. Here's another option, question answering. The dynamic memory networks paper, the aim there was to try to create a generic architecture that is applicable to a number of different NLP tasks. Their claim is that most, if not all, NLP tasks can be translated into a question-answer format. This is kind of where my idea of, well, let's just entertain what would it look like if we take our tasks and then try to translate those into something that's somewhat non-intuitive. So again, the same request. We now have a set of assertions: fly from Berlin to Helsinki, fly early in the morning, and so on, and then a bunch of questions and answers to those. Again, the problem here is that it's not entirely clear to me how to translate that original text into that set of assertions, or at least that would be another prediction problem that I need to solve before I can solve this problem. Possibly we could actually just feed the original text as it is to the model. If you have any experience with these, I would love to talk to you. And then finally, this is kind of the very, very traditional NLP approach. So we have an input sequence and we have an output sequence that is exactly the same length. So for every token, you produce an output token. This is, for instance, what named entity recognition does, but in our case, we're not outputting named entities, we're outputting these labels for, well, this is the origin of the flight, this is the destination, this is the departure time, blah, 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 blah. And then there's a bunch of tokens in there. There's a bunch of words in our input that are completely meaningless, so we just label them as O. The problem here is that the way in which we need to combine, because if you look at morning and early on the 10th, those go into the same slot, but they're separated in the input and the output sequence. So we need to add lots of logic on top of this before we can actually say that the departure is early on the 10th in the morning, not, for instance, early in the afternoon of the 10th, which would also be a possibility. This is incidentally what we are actually using. Okay, so a few considerations that we need to pay attention to when we're looking at some research and entertaining whether we should even look at it. How well does the model fit to what we need to do? Another way to think about this is how convoluted do we need to make the evaluation before we can get something meaningful out of it? Think of the question answering task, where in order for us to use that kind of an approach, we would actually need to have possibly a secondary task that we solve before we can solve the actual task. That's a very convoluted way of thinking about this. How well can we identify, isolate, and fix errors? Any model that we do produce is going to have some errors. And we need to be able to, identify, isolate, and fix them, ideally. So if we have one huge model that solves the entire problem in one go, any change that we make to that model is very likely to introduce some regressions somewhere else that we didn't intend. So thus far, we've kind of gone with trying to pick apart the models and rather apply a sequence of models than try to encapsulate everything into one single model. The problem with that is that the errors between the models tend to multiply. So if we make an error very, very early in the pipeline, then everything else is somewhat meaningless. There's, of course, deployment costs. We need to be aware of what the memory requirements are. We need to be aware of, do we need specialized hardware? And then, is there a reliable implementation available? A lot of research nowadays in NLP tends to have some implementations available. Some of them are quite wonky and you really don't want to use them. Some of them are not. Maybe there's others that I forgot to mention. This is what then, sort of looking at what we currently have in production. So we have kind of two main tasks, or two main levels of looking at this problem. Document level classification. We have three classifiers there. There's a booking classifier. Does this message contain a booking, or does it not contain a booking? Is it, I don't know, is the customer just wanting to change their address or a frequent flyer number, or is it a cancellation, or do they actually want to book a trip? What is the content of that booking? Is it a flight? Is it a hotel? Is it a combination? And then finally, is it in scope? We're not even trying to handle bookings that contain 15 different flights and 2 trains for 17 different people. That's, if we see something like that, that's just passed on to the human travel agents immediately. The model that we're using is the model from the Bag of Tricks for Efficient Text Classification. There's kind of a cartoonish version of what it looks like, but that's actually the model. This is super simple. It's very easy to implement. It has relatively low memory requirements. It's very quick to train. And it works really well. We've been looking at lots and lots of way more complicated models with language models and all kinds of stuff. We've been completely unable to find anything that, there's lots of things that match the performance of that in terms of just raw metrics, but they also take a week to train. So thus far, we've just been sticking with that. Then the information extraction or the slot filling task. We currently have a really weird model that was inspired by some Kaggle competitions in the past. Don't pay any attention to that. I made it extra small so you can't read it. It's a convolutional neural network that does feature extraction and then like a recurrent neural network on top of that, which makes absolutely no sense to me. That's going to go away. We have this the model from the researchers at Zalando. We have already tested that. I'm currently training a full sort of production version of that model. We know that we get a lot better performance out of it. So this is absolute improvement of about 13 percentage points in F1, averaged over 71 labels. That's well, at least for us, that's a very, very significant improvement in performance. The only downside is that it takes a week to train it on a GPU machine. And then we need a GPU machine to deploy it, and so on. But it does much better. There's a bunch of models, or there's a bunch of problems that we haven't been able to find anything in the research field for. One of the main ones is time expressions. These tend to be extremely difficult to find and interpret correctly. So we were using a solution from Facebook before, but then we built our own, which is called CT-Parse. That's an open source library. If you want to look at it, you can find it on GitHub. It works very well for us, but it is targeted for our use case. So if you want to use it for something, minimum requirement is that all of your time expressions point to the future. We do not handle the past. No one wants to book a hotel for last week. There's a bunch of ongoing research that we're looking into. A lot of it is for the document level classification. We're just sort of trying to tie up some loose ends and figure out if we can't find anything better than the fast text or the bag of tricks. Time parsing, as I said, there's a bunch of stuff that I'm looking into in terms of the sequence prediction, the slot filling task. Mainly there as well, so the top thing there is tight coupling with pre-trained language models. The model from Zalando research is going to go into production, but then there's a whole bunch of other stuff that we still need to look into and make sure that those aren't better. And yeah, time parsing. Recommendation is one. We are hiring. If you have any interest in NLP and recommendation systems and really complicated data sets, come talk to me. Here's some pitfalls to avoid. Start with really, really simple models. Don't take the latest research, just take something that you know is going to work. and establish a baseline. If you don't have a baseline with a really simple model that you can run on your laptop, you have absolutely no idea how anything stacks. You don't know what you should do. State of the art is often, it's the way the academia works is often very misleading. Just getting half a percentage point of an improvement on the state of the art is often completely useless for production. We don't care, because there's so many different other considerations that we need to take into account that half a percentage point on some specific task, on some specific data set, all of that goes out the window once we incorporate everything else into it. One part of that everything else is that because we're trying to create this booking, if we get one single slot wrong on a request, the rest of the request doesn't matter. If we don't understand what the destination of the flight is, it doesn't matter if we get the departure time correctly. And this is where the academic evaluation measures are often very misleading for us, because they don't take these sort of, I don't know, like hierarchical evaluation measures often into account. They're focused on the document level or the token level, but we need to kind of pay attention to both at the same time. Once you have a baseline, don't be afraid to have just completely crazy ideas. Even if it doesn't work, it's going to further your understanding of why it doesn't work, what the data looks like, and at least it's fun to think about some other things while your model is training. Here's some recommended reading. I would actually even recommend that you read it in this specific order. The NLP is ImageNet Moment by Sebastian Rurer. That's a really, really good overview of this whole idea of training these language models. Then Generalized Language Models by Lilian Weng is a much, much more in-depth view of like how specifically do these models work, each and every single one of them. And then finally, once you've gotten yourself really excited about how everything's going to be great in the future, please go and read NLP's generalization problem and then sort of come back down to earth. I apologize for being over time. For those who have been, thank you for listening. The work isn't done alone. That's the rest of the team. We are a fairly small bunch, at least for the time being.